talk that will given by our beloved host, Tara. And Tara, are you there?
Yeah, I am here. Thank you, Lulin. And am I audible?
Yes, you are. We can hear you.
Yeah. You can't hear me?
Yeah, yes, at least I can hear you.
Okay, fine. Yeah, I thank you, Lulin, and giving me this opportunity to present a cloud seeding case from the KIPEX experiment that we have conducted recently. I just want to first thank authors here, but they're all, most of them are my colleagues, and I also want to thank Daryl. He has been instrumental in understanding some of the urban observations, and the last author is our director. And so here, basically, we have the KIPEX is about understanding clouds, their physics of clouds, aerosol cloud interaction, and as well as what will happen if we seed the cloud, whether how exactly the physics of cloud seeding works, and whether we can formulate any guidelines based on the observations we have done and the findings we have. So basically, today I want to talk about glaciogenic seeding in the embedded convection within altostratus layers. This is typically seen over over our study region. I will explain to you our study region. We have made a big observatory in our study region with C-band radar, and we have been flying aircraft, and we also have a ground-based aerosol observatory and thermodynamic and other boundary layer measurements. So all of this today my presentation will be only to describe that case. I'm not really talking anything about the model. So basically, this is the region that I am talking. You see this oval area here, and this is we are having the Western Ghats mountain ranges. So it is situated like that, and you see the rainfall. This is the TRMM rainfall over several years, daily rainfall climatology. You see the most of the rain falls on the west side of the mountain, and we are having a rain shadow region here. So the many of the state governments are interested in conducting cloud seeding, but there is no scientific basis for that. So the government, our ministry has decided to have this scientific investigation of the cloud seeding. So our experiment also focused on the physical evaluation of the cloud seeding, that is by seeding and then making observations with the aircraft, as well the microphysical observations, as well as with the radar observations. So I will present one case. Here I'm talking about the 11th July 2018 case. It was an active monsoon period, and we have layer clouds, shallow cumulus and nimbostratus clouds. Actually, it was the formative stage of the nimbostratus clouds. So the interesting point here for me was that the seeder feeder mechanism was active in this particular case. So what you see here is the WRF model reflectivity at 1 kilometer resolution. That is at 1 kilometer height, 2 kilometer height, 3 and 4 kilometer. You can see the different types of clouds are popping up as you go from the surface from at different altitudes. So this particular case, if you look at the thermodynamic condition, you can see small cumulus in the lower layers. At 1.5 kilometer, you have the boundary layer situated, and between the boundary layer and the 4 kilometer, you can see a dry layer, and above that, this stratus layers are there. This is indeed consisting of both liquid as well as ice. That's why, that's why it's quite important that we understand the mixed phase processes in these clouds as well. So one very peculiar characteristic is that we have a low-level jet. It is the monsoon low-level jet, which is actually, so in this observation is with the aircraft, so you will see very high frequency measurements here. So there are wind speeds up to 20 meter per second. Actually, it is just around the height of this this shallow clouds that you see the peak of the core of the low-level jet. So above that, we have a strong shear where we have the easterly jet, actually much above this height, but our clouds are below that level. So this is the wind and the temperature observations that we have taken with the aircraft. So I just show one east-west cross-section of the vertical cross-section across the region from the radar observations. Radar was situated at the center of that region, the rain shadow region. And towards the left side, you have the Western Ghat mountain, and towards the east side, you have the free land. So what you see here in the first plot is that it is the radar reflectivity. You can see very typical patterns like the wavy type patterns that are seen. Actually, these clouds. These are the regions where the clouds are present. So that's why we get some signal here. And then you also see the CDR values here. It's a dual polarized radar, and also you can see the wind. Wind is indicating this jet core over the region. So basically, this orography is indeed having a significant impact on the clouds over the region, and they are also indeed influenced. They are very much dynamically driven as well. So this is a visualization of that same case during the 2 hours, 7 UTC and the 8 UTC. 7 UTC is the time that we have had aircraft observations. That's why I'm showing this particular plot. So in the lower layers, you can see shallow clouds. These are these white patches that you're seeing. And the upper layers, you see the ice clouds or the mixed phase clouds. And they are distributed in an uneven way. And as well as you can see the colors are the updrafts and the downdrafts. Only updrafts are shown here. And there are also some trajectories shown, and which shows these wavy patterns, which is again indicating the importance of the dynamically forced situation here with orography. So, and with time also you can see that the cloud patches are moving inland. Okay, so now coming to the aircraft observations. What you see here on the top, it is the accumulated rainfall over for that particular day, and the red lines you see are the aircraft track. So we made, when you see so many such lines here overlapped, we made several passes in that particular cloud, and we made, I must say that we made nearly 112 cloud penetrations for this particular flight, and that was between 3.2 and 7.8 kilometers, and we went down to minus 17 degrees C, and the relative humidity varied between 60 and 100%. So I have indicated a few locations where this is the time trace of that temperature and the humidity, and you can see ABC where we have we have indicated we have done some cloud seeding with the glaciogenic ejectable flares. Okay, so after, so we have how the strategy we have taken is that we find convection that is popping up above the stratus layer that are actually we are not seeing any precipitation yet. Such layers we have found, and there are convection popping up. Those convection we pass through initially and then see if it is having some reasonably good updraft. Then we are choosing such spots where there are embedded convection, and then we put this the ejectable flares into those convective area by going a little bit above that convection. So I have personally been in this flight, so that is also the reason why I am just talking about this one. And after doing that one seeding event. See, this is one example of that seeding event. This is at a high altitude, like 8 kilometers we have gone. And then we have done the seeding event here at this particular point, and then made the observations down. And at different, actually we have come through that stratus layer in many passes. So you see in the lower plot, you see the liquid water content. And the upper plot, you see we have done some Cvi measurements with the SP2XR instrument, where we can look at the scattering as well as RBC particle number concentrations. So our idea is to trace that seed particles if they are present at lower altitudes. So we have got some signal, but we can see that each and every penetration we can see that signal, and it is reducing at lower and lower altitudes. So again, these are all the velocity. Interesting point was that updraft and downdraft, maximum updraft and downdraft are shown. They were quite large in some of the cloud passes, and of course the winds were quite strong in this particular case. And also, I have also looked at the cloud drizzle and rain number concentrations here on the right. This also has been investigated after seeding. We see a slight enhancement in the number concentration after seeding in many of the passes. So this does not have a title. Sorry about that. This is a cloud pass we have done at 8.5 kilometers. This is just before the seeding event, and then we have used an ejectable seeding. And then we made passes at different lower altitudes. Like this is at 7 kilometers, the lower plot. And you see the radar reflectivity on the left. Then you see the hydrometeor classification on the right. And also the images from the cloud probes. This is the blue ones are from the cloud imaging probe, and the black ones are from the precipitation imaging probe. So you can see a different snow, or you can also see some super cooled drops here, this donut shaped, So there are different processes that may be contributing here. The interesting thing is that this particular case had a lot of supercooled liquid present as well. So then going to the next couple of other lower altitudes like 6.5 on the top and 5.5 in the middle and the 4.5 at the bottom. So you can see this is indeed leading to, here again the supercooled liquid is present as well as some aggregation is also seen here, and you can see some snow. And then at 4.5 kilometers it is all drops. So basically, this is the time that we have passed. The freezing level is around 5 kilometers, and we have passed that, and we incidentally we see drops falling. So if we look at this information, that was from this was from the when you look at it in an XY plane. But if you look at this in a vertical plane, you can see this is the first set of images are for the around the seeding time. Seeding time was around 9:30 UTC, and this is 9:29, and then 9:38, and we made these RHIs, means across this region. So we could indeed see some of the clouds made precipitation, and then something interesting happened here. You can see initially there were the lower plot, if you see, it has got ice particles at the top, and then there are some aggregates which was also seen by the aircraft observation. Then there is snow, wet snow, and then there is raindrop. So this has after the seeding, we don't know whether it is really due to the seeding effect, but we can see there is more raindrops forming in that seeded area. And also we can see that there is a enhancement in the ice, the aggregation and the ice in this. And also the cloud had gained a little more depth over that during that time. Then we also looked at the precipitation, precipitation from the radar, from the seeding location, downwind of the seeding location. So basically we have such observations also from the rain gauges, and this is just just to give you a glimpse of what kind of observations we did and what is available. So then from what has been found, a particular concept is made from whatever is seen. See, on the left you see the aircraft is indeed finding out these convective elements in the stratiform cloud, and doing the ejectable seeding. And once the seeding material, and at this time the cloud is not yet raining, there are layer clouds, and after the seeding, actually we see some kind of we call this as CDR hats. We have named them like that because there is an enhancement in the ice particles in this region as per the radar observations, and we could also see that in the in situ measurements, and when we come down further in this layer, we have also seen some Hallett-Moser process. These are actually the real pictures from the SIP images, and how the raindrop has formed in this cloud. We could document that from the in situ measurements as well as from the radar observations, and then there is an aggregation process and the melting, and then then these more collisions and then making more rain possibly. So the one aspect I have noticed in the experiment was that whenever we are going, there are large drops already present in some of these shallow clouds. So how do they really form? Where do they come from? See, basically they are very thin, shallow clouds, but we see very large drops most of the cloud penetrations there. This could be a mechanism which is indeed contributing to that, and since we could register the microphysical structure in and a conceptual way, we could look at this. I feel that we could do some modeling studies of such a case and see whether we can investigate the seeding impact. So that's why I have presented this. Thank you.
Thank you, Tara, for the very comprehensive description of these case. And we do have time for a question. All right, let me first, Arunda Dati, you are spotlighted, and you can unmute yourself.
Hello, Arundhati.
Yeah, she is spotlighted, but just she
Hello?
hasn't unmute. Oh, okay, now
Yes, you can talk.
Okay, ma'am. It was a nice presentation to see that after seeding, there are some changes in the cloud parameters, and we could say that this seeding is definitely changing something inside the cloud processes. But one thing I'm curious about, when you are doing the seeding, how to know that in which direction the cloud development might occur? Is it the dominant wind controlling it, or there could be something else also?
Yeah, thank you for the question. Actually, we have all observations and the GPS on board the aircraft, which will indicate the position, and we can indeed follow one cloud. We can the same cloud we can follow by knowing the location of that cloud, and we have done several such instances. We have followed the same cloud. So basically, that is one advantage that we can indeed identify which region we have done the seeding or which cloud we have targeted, and just like that, we will not conclude something. So, and simultaneously, we are looking with the radar observations also. So, both together, we can find out that it is the same cloud.
Okay.
I hope I answered your question.
Yes, ma'am. I understood. Another thing I want to ask regarding the same question, that is, ma'am, you have done so many cloud seeding programs like in different years. So, like, did you find consistency in the direction of this cloud configuration? Like the earlier question I asked regarding the
cloud invigoration. I don't want to talk anything about invigoration here right now, because see, the point is that definitely clouds are influenced by aerosol. That is proven. And
Yes,
seeding
definitely.
is nothing but you are introducing a specific type of aerosol into the cloud, and whether that seed particle has gone into the cloud, you have to first make sure about that. And if you don't make sure, and then you draw your conclusion that okay, this was due to seeding and that was due to seeding, that does not make sense. So basically, we have to make sure whether the seeding is done in the right place, the right time, right cloud, and whether the seed material has gone into the cloud. And are we seeing the kind of characteristics that we expect from the textbook? Whether are we seeing, see, here we have done the glaciogenic seeding, so we are indeed trying to see if we can get more ice particles into the cloud, right? So
Yes, yes.
these questions have to be answered by looking into so many details. Just like that, invigoration we cannot say. Cloud must have
Okay,
grown
ma'am.
due to some other reason also.
Yes,
Yeah,
yes, yes.
thank you.
Yes, ma'am. Thank you, ma'am.
Any thoughts, comments, and questions from the audiences? I believe Weicha has a lot of things wants to say, and before he raised his hand, I would like to comment on the approach, or at least the strategy of looking into the seeding signals from the clouds. So Tara, I really strongly appreciate all the efforts that the team put up to collect so many different observations from multiple multiple platforms. But I noticed that you did pick a cloud is more complex, in my opinion, that have like multiple layers and being influenced by not only just the jet itself, but also the mountain on the west in the west. So by combining so many different uncertainties or forcings, that such clouds has its own kind of evolution, lifetime, and patterns that has not been fully understood yet. And then when you on top of this many uncertainties, you try to see the cloud and identify the differences, becoming more challenging. So in general, I think if you want to find especially the physical responses of cloud to seeding, maybe the best strategy is to pick the simplest cloud as isolated or as stable in steady state as possible, and so that you do have a more relative low variability, natural variability in that case, in a sense. And then when you perform a cloud seeding in well-controlled kind of a manner, and then with multiple angles of observations, you are having more opportunities and chances to isolate them and at least to identify these signals. So we have done a lot of researches in the glaciogenic seeding in the Western United States, and we do know for the very stable orographic cloud, we're able to observe the seeding signals and also simulate them. For more complicated cloud like what you have probed and what you have seeded, is really challenging. So just don't know by looking at this specific case, do we really able to tease out the signal? But if you want to do model simulation for such cases, I do think we want to kind of make it more idealized and for certain part of the cloud and see if anything we can find. If we simulate the whole case, I think like what Weicha said, you have to do multiple ensembles to really quantify your seeding impact.
Yeah, definitely, Lulin. Thank you for the comment. Actually, our main focus was on isolated clouds. I have not presented that here. Isolated, shallow, immense, cumulus, like the warm-based clouds. Most of our observations are done in such clouds, but the interest with this particular case study was that this is a common case observed during the active monsoon period, where this seeder, even not in respect to the seeding per se, but overall, this type of cases are quite relevant for understanding the physics and understanding the processes that are driving the precipitation. So see, I chose the complex case, but but it was just to tell you, give you a little introduction about the kind of situations and the kind of environment that is there. So it is not it's not just to complicate the things, but I do understand and appreciate that this has to be done in a very like idealistic way. Initially we should understand, and then maybe we should go into more complex things.
Yeah, thank you, Tara. In the interest of time, we want to move forward, but it's great that we see so many observations available for your program. So
Yeah, thank
would
you.
you mind? Yeah, would you mind unshare your screen and we'll move to next speaker, CC. Our next speaker is CC Chen, our one of the PyChamber case leaders, and she will talk about some DNS and puzzle simulations for different seeding scenario. Here we go, CC. You should unmute yourself, CC.
Talking to myself.
Mm-hmm.
Yeah.
All right, here we
Can you see my full screen?
Yes.
Great. So first, thank you very much for offering me this opportunity to present our recent research on hygroscopic seeding simulations using puzzle model and the direct numerical simulation. Before I start, I want to acknowledge my collaborators, Lulin, Sarah, and Courtney, Rulof, Roy from NCAR, and Peter from McGill University. So hygroscopic seeding introduces relatively large salt particles into the clouds. So in the conceptual model for hygroscopic seeding, those type of particles compete for more water vapor and suppress the growth of the small droplets. This is known as the competition effect. And on the other hand, the large seeding particles are easier to form big drops to kick off the effective collisions. Ideally, they could enhance the rainfall on the ground. But in reality, even though the conceptual model has been proposed for decades, it is challenging to obtain direct evidence from the observation. The contradicting results from the field studies are partly due to the uncertainty in the measurements and the instrumentation errors, especially for the seeding in the convective clouds. The variability of the convective clouds are really high, and also we have a high variability in the aerosol conditions as well. So therefore, in this context, the numerical models with constraints from the observations become valuable for evaluating the seeding impact, and it can create well-controlled conditions and also relatively realistic conditions and provide a process-level understanding of seeding effect. So one interesting study we conducted was to use a puzzle model to represent and analyze the hygroscopic seeding impact and compare it to the measurements during the Queensland Cloud Seeding Research Program. The first goal, or the main goal, is to verify whether such a simplified 0D model can capture the main trend observed by the flight measurement. So the field campaign provides the aerosol size distribution in different aerosol regions and also the cloud-based condition. We picked the two aerosol size distributions representing the continental and the maritime influenced condition. The main difference between the two was the chemical composition and the concentration of the coarse mode aerosol, which in maritime condition, it contains more sea salt aerosols. We also have I-70 seeding size distribution available from the wind tunnel measurements. So the puzzle model is Lagrangian in nature, as we are following the air puzzle's trajectory. We use moving beam method to calculate the evolution of droplet spectrum, so the numerical diffusion was reduced. the seeding was implemented at subcloud layer, and an updraft was prescribed to bring the parcel into the cloud. DSD near the cloud base was analyzed to evaluate the cloud seeding effect. We conducted an ensemble of parcel model simulations that experienced different updraft velocity and different seeding number concentrations in order to investigate how those different conditions influence the seeding effect. We performed the 2 dilution scenarios where the low dilution corresponds to a higher seeding number concentration. The no seed case is our control experiment. The figures show the droplet size distribution at 400 meters above cloud base in the continental influenced and the maritime influenced region. Overall, we can see the seeding effect is more pronounced in the continental clouds compared to the no seed, as we see in the red histogram. The seeded size distribution is broader, and overall the concentration of droplet over 10 micron in radius are also higher in seeded clouds. In contrast, if we look at the maritime influence, the DSD, they did not show a substantial broadening in the seeded condition. And the cloud can already produce a relatively wide tail without seeding because of the abundant large sea salt aerosols in the background. It is also noticed that the seeding increases the droplet between 15 and 35 microns, which are important sizes for the collision coalescence in subsequent cloud development. We also look at the effects of updrafts. It is found that the DSD is broader in the weaker updraft condition, as shown in the red histogram. Even though this weak updraft produces a relatively lower supersaturation, as shown on the right, a weak updraft corresponds to a longer time for droplets to grow before they reach to the same height. Therefore, the overall effect for the updraft is that weak updraft has a higher growth rate with respect to height, therefore producing relatively large droplets and a wider distribution. This indicates that growth of big drops may be less susceptible to supersaturation and more sensitive to the in-cloud residence time. Meanwhile, we see the aerosol activation is more sensitive to the supersaturation. The plot shows the number concentration of activated aerosols varied with updraft. A high updraft can produce higher supersaturation, therefore more droplets are activated. Therefore, the impact of updraft has two folds. And first, it modulates the supersaturation, which is critical to the activation of small particles. It also determines the air parcels in cloud residential time, which is important to the growth of the big droplets. So here is the summary for this parcel model simulation. And this study has been published in JGR. And I also have a poster session on Thursday if you are interested to have more discussions. So in the parcel model, we know the particles are uniformly distributed inside the domain, and all droplets experience the exactly same environmental condition. But clouds are relatively turbulent, and the small-scale fluctuations may have prominent effect on the particle growth. Therefore, DNS can help with this type of process, and the direct numerical simulation resolves the finest scale of turbulence, and it can help us to better understand how city particles interact with and/or affect the immediate environment, as well as affecting the natural cloud growth. The model is able to accurately trace in individual particles and simulate the droplet collision and the condensation as they interact with the turbulent moist air. So we designed 10 idealized simulations. The no-seed case was given as a controlled experiment. The nine seeded cases has 3 different particle sizes and 3 different number concentrations of the seeded particle. So those 10 cases were given the same cloud-based condition and sent to the clouds the same way as we designed the partial model simulation. So here is the droplet size distribution of the 10 cases. The color denotes the number concentration, and vertical chords are the radius and horizontal time. So the no-seed case is on the upper right corner for comparison. As we increase the seeding particle size, we can see mode separation between the background aerosol in the bottom branch and the seeding particle size distribution in the upper part. So we can see the same response in the mode separation if we increase the number concentration of the seeding particle. So in general, we see if aerosols are small, for example, in the first column, we have 1 micron of seeding particles. Their growth are slowed down after droplets are formed, as we can see this slope, a shallow slope, because of the reduced solute effect. However, for large seeding aerosols, as shown on the right panels, in general, they remain a relatively high growth rate by condensation throughout the time. So this indicates that the solute effect still play a key role after becoming droplets. Therefore, this has implication that the beam microphysics that ignores solute effect after the activation may underestimate the seeding effect from those giant particles. We also found that in regions free of entrainment and or large-scale mixing, supersaturation fluctuations are fairly small. The left panel shows the PDF of supersaturation fluctuations of the 10 cases. So if we see the x-axis, their magnitudes are very small compared to the mean supersaturation, which is around the order of 1%. This situation is not like the pie chamber case, as we showed on the right. The fluctuations can go up to several percent due to the strong mixing between the warm bottom and the cool top. Therefore, in adiabatic cloud case, if we look at the small scale impact of fluctuations, the mean supersaturation plays more dominant role than the fluctuation in droplet condensation and the aerosol activation. So here is also my summary for the DNS study. I will stop here for the question. Thanks.
Yeah, thank you, Ceci, for the great presentation. We have about 2 or 3 minutes for questions and comments. Anyone wants to raise your hand? I can spotlight you. Do you have a poster or talk on the second part of the?
No, I don't have that. Yeah, but I will be here in ICCP for the whole week.
All right, here we have a hands raised. All right, Dr. Mathu, you are spotlighted. Please unmute yourself.
It's a very good presentation. I just want to see that 2 slides back to the end, 2 or 3 slides back, you have shown that cloud to rain transition. Yeah, this one. So it is showing that the cloud droplets become a rain droplets is after 6 to 8 minutes. Is it like that?
So it depends on how the seeding number concentration and the radius. So in the if we have the biggest seeding particles, then yes, it will even form range of after 4 minutes. We can see that here. Yeah.
And who is mediating whether how the cloud droplets become a rain droplet? Have you find out who is the important contributor? That means I mean to say the cloud turbulence or something.
Oh yes. So in this case, I think the turbulence plays a key role because we are using the mono dispersed. In the stagnant air, it's hard to collide. But we can see from this broadening of the tail, it's mainly contributed by the turbulent collisions between the similar sized particles. So
excellent.
Yeah.
So we have seen actually we are having a cloud radar which can see the smallest cloud droplet particles. We are also find the near same thing like 6 to 8 minutes time it is required after a turbulence initiation. It's a trigger, and we are getting 8 minutes. It's a nice. I think it's a direct evidence. Nice. Thank you.
Thanks for the information. That's good to hear.
Great. If we don't have any more questions, we'll move on with our next speaker. Our next speaker is Ishvan Garashi from University of Lepage, Hungary. Ishvan, are you there? You need to come up to the speaker podium.
Oh, sorry.
Yeah, you need to move around. Yes, coming up and stand on the speaker. Oops, you are too far.
I am here. I'm there. I don't see.
No, not yet. Yeah, can you come down and then go to the right?
Okay.
Yes. Yeah. One more to the right.
Okay.
Stand on the sign.
Okay.
Just
okay.
A little bit too much. Okay, here, right here. Sorry, make it difficult for you. All right, here you are able to share.
Yeah. Oops, something is wrong maybe.
Okay.
So, can you see my screen?
Not really.
So I try to. Yeah. I click a window and click on the share. Yeah, so that it is written that I need permission to access.
Okay, let me show your presentation and you can.
Okay, that's great. Thanks, William. Yeah.
Okay, let me share my screen. Here we go. And can everybody see the full screen now? Okay. Yeah, Ishvan, you're able to go ahead. I will forward the slides for you.
Yeah. Okay. So I see my and you can show. Okay. Thank you, William, for your help. So as I was asked to have a presentation about the application of the beam schemes to simulate the weather modification, the impact of the weather modification. I will speak about two different topics. One is, William, please, the next slide. So I will speak about two different topics. So one is the glacionic seeding. So it is a simulation of the impact of the weather modification, impact of the AGI seeding. And this project was a part of the Wyoming weather modification pilot project. And so the microphysics scheme was implemented into the WRF. And we used the WRF to make a 3D simulation about how the seeding can impact the amount of the surface precipitation. Please, the next slide. And here you can see the summary of the description of the bin schemes we use. So that's this the characteristics of the model is well known, I think. So we have water drops, pristinized snowflakes, and graupel particles. And one important thing I have to mention that we have two different type of water drops. I will mention later why. And after that, you can see that's what type of process are involved in the simulation. And finally, you know that we use the two-moment conserving technique, like as it was published at Cvi et al. Please, the next slide. Okay, so you know that it is important to know it's how the ice nuclei, that's I mean the artificial ice nuclei, can impact the precipitation formation. And so here you can see that we simulate the deposition and condensation effect, and also we simulate the contact freezing effect. And here you can see also why we have two different type of water drops. The reason is that this way we can able to tracking the silver iodide particles inside of the drops. So this means we can simulate the immersion freezing initiated by the silver iodide particles. So that's the short summary about the model. And please, the next slide. Okay, so here are the results. So we chose 4 different cases. It was part of the randomized seeding experiment. You can see here the 4 different cases. We simulated these cases, and we made a sensitivity test. It means that we used 2 different CCN concentration and 2 different function, which describes the temperature dependence of the activation of the ice nuclei, natural ice nuclei. And I mean here there's the activation of the deposition nucleation and the condensation or freezing nucleation of the natural ice-forming nuclei. Next slide, please. So here you can see a comparison with the observation. So because this project has a number of observation about the surface accumulated snow, amount of the snow. So we were able to compare the observed data with the model data. And here you can see the results about the comparison. And the horizontal scale shows the observation one, and the vertical the simulated one, and the different color shows the different rain gauges, snow gauges, sorry. And so if you see that's this line, which is the 1-to-1 line. So here you can see that we were able to simulate relatively well all of the cases, but one. That means that's only this. That's the simulated randomized seeded experiment 114. So this was the case. We have some station which are out of this line. So this case is the simulation was not so good, but there was some question about the representativeness of the snow gauges as well. So please go to the next one. Okay, so here you can see that's the simulated precipitations, accumulated surface precipitation, and 4 different cases. And it was in the first column. In the second column, you can see that's the difference between the seeded and the control cases. That means that's the red color shows that's the enhancement, and the blue shows the region when the snow amount of the snow decreased due to the seeding. And you can see here, if you see that's the clean and IN1 and clean IN2 in the second and the third column, it means that's with the different CCN concentration and different temperature dependence of the activation of the ice nuclei. So if you see this figure, so you can see that we have a significant effect in the second row and the third row. And if you see the last row, it is interesting. I have to mention that if you compare the two effect, then the third and the second and the third column, it means that the reason of the difference is that the source of that's a ground seeding generator was moved to the different location. You can see that the sign plus means the location of the generator. So that's the different effect is the consequence of the different location of the ground-based generator. Next slide, please. Okay, so now we look forward, so how we can explain that sometimes we have a relatively large seeding effect, and sometimes we don't have a seeding effect. And so here you can see some explanation for it, what we do. So this figure shows that's the vertical profile of the horizontally integrated liquid water content, and the direction of the horizontal line is the propagation of the reagent. So that it describes the environment of the spreading reagent. And here you can see, if you see the horizontal axis, that's the range of the horizontally integrated liquid water content. And in the first case, you can see that's the amount of the liquid water is relatively small. And if you go, if you see the last one and the first one, so here we can see that the liquid water content is significantly larger. So that was we found. So that's we can found the relation between the seeding efficiency and the amount of the liquid water content. But it is important to emphasize that here it means that's not the vertically integrated liquid water content, but the horizontally integrated liquid water content. And the explanation is that, so this gives the propagation and the moving of the snowflakes. And this way we can describe the environment of the snowflakes. And if the snowflakes feel a lot of liquid water, they can grow faster and they can become larger. And if the liquid water content is small, the snowflakes remain small. So that was we found. And please go to the next slide. And so here you can, if you see the figure A, so it means that the horizontal axis, you can see that's the precipitation efficiency of the control case. That means that's what is the ratio of the condensed vapor and the surface precipitation in the case of the control simulation. And the vertical axis shows that's the impact of the seeding. So that means that's the ratio is equal to 1. That's the vertical axis. You can see the 1. It means there is no seeding effect. And if we go up, you can see here that, for example, in the case of the 1.07, it means that in this case, the seeding increased the amount of the precipitation by 7%. So that's the figure, the dots in the figure A shows that there is no straight relation between the precipitation efficiency in the control case and between the efficiency of the control case and the precipitation enhancement factor. But if we move to the figure B, so we can see a more straight relation. So in the horizontal axis, you can see the meaning of the axis gives the enhancement of the diffusional growth of the snow due to the seeding. So that means you can see that due to the seeding, there's some case, there's the diffusional of growth of snow was enhanced by 20%. And that means, that it gives the largest efficiency of the precipitation enhancement. So this figure tells us that the enhancement of the diffusional growth of the snow has a strong relation with the precipitation and the efficiency of the precipitation enhancement. So this is the main message of this, that that's the amount of the liquid water content is high enough. So in this case, that's the environment of the snowflakes is good to promote the diffusional growth. And it is also important to mention that that's the large amount of the liquid water doesn't mean necessary that the rhyming increase efficiently, but the diffusional growth also. So that's the summary of this result. Please move to the next one. Okay, so now we move to the other type of seeding. So this is with a simpler background and simpler dynamics. And Ceci mentioned in the previous presentation that he used the parcel model to describe the formation of the precipitation in the case of the hygroscopic seeding. So we do the same. And please, the next slide. So here you can see the description of the model. As I mentioned, we use the 1D parcel model. So that's we use the prescribed updraft velocity. And here you can see that's the beam microphysics scheme. We use 70 beams to describe the microphysics. And we use different categories. So not only we have a difference between the sizes, but we have also different depending on what type of aerosols are inside of the water drops. So as you can see here, you can see a solid line curve and a dashed line curve. So that means we have different categories depending on what type of aerosol particles are inside of the drop. And the difference is that what is the hygroscopicity of the aerosol particles inside of the drop. So this means this we made two different categories in the case of the background particles, because we have different hygroscopicity for the fine particles and the coarse particles. And depending on the seeding material, we have 1 or 3 categories for the drops formed on the seeding materials. It depends on how many different types of hygroscopicity are used for the seeding material. So this is the short summary, and one more slide about that. So we use that's the microphysics. You can see that's what type of microphysical processes are used here. The diffusional growth, of course, is used for the water drops, and we use both moving and fixed beam. And when we take into consideration the curvature effect and the solution effect, so in this case we use only the moving beam scheme, but when the drops became large enough, so when we can neglect both the curvature effect and the solution effect, in this case we move to the other type of description. We use the fixed beam, because the fixed beam has a lot of advantage about the description of the collision coalescence of the water drops. Please, the next slide.
Yeah, Ishvan, let's try to finish within 3 minutes. Is that okay?
Okay, sorry about that. Okay, that's so fine. Here you can see that's the what is the prescribed updraft, and here you can see that's how we describe the different type of moving beam and fixed beam. So this here you can see here's the cloud base, and we start to simulate the growth of the drops well below the cloud base. And please go to the next slide. And we made a number of sensitivity tests, about 100 cases. We discovered different type of seeding material. We use different concentration, updraft profile, and so on. Please go to the next. And here you can see the impact of the seeding. So that's in the first row, you can see how the nanoparticles mean in this case, that's the size of the average size or the mean size of the aerosol particles, about a few microns, and the hygroscopicity is large. So in this case, you can see that's the impact of the seeding, and you can see that the nanoparticle results in a relatively results in wider size distribution. And we can see that's the second row. That's the seeding is relatively small when the seeding material contains mostly fine particles. And this is the last.
Sorry, we cannot see your slide.
Oh, sorry. Oh, sorry. Oh, sorry. Lulin,
Yeah,
please.
Lulin, can you share your screen again?
Yeah, I
It's
think
not
my
shared.
screen kind of went out somehow. Sorry about that. Here we go. Can you see it?
Yes.
Yeah, okay. So, Lulin, I think that I don't know how you be sorry because I don't see that's what is on the screen. So I mentioned the results, and I mean that it was a slide 14, and now we have a slide 15. So this is size distribution. Is it okay?
Right. Yes, I think you just described the size distribution slide.
Yeah.
Yep.
Okay, so that's here you can see that's the impact of the seeding with two different type of particles. The nanoparticles means when the average size is about 1 or 2 micrometers, and the hygroscopicity is large. It's above the hygroscopicity of the salt particles. And the second row shows the impact of the seeding when the seeding material is contains mostly small particles. It means that they are fine particles, so their average size is 0.1 micron. And here you can see that the nanoparticle results in a relatively broader size distribution, and the impact of the seeding material, if you use the fine particles to seed, is almost negligible. So the different columns means different background aerosol particles. So here you can see that's how if you see the impact of the background particles, so it also impacts the efficiency of the seeding. And we have only 2 more slides. Please go to the
16.
Last but one. Okay, so here you can see that's how we try to estimate the impact of the seeding. We introduced 2 parameters. So here you can see the HC describe the impact of the coarse particles. So NC means the concentration of coarse particle. Kappa C means the hygroscopicity of the coarse particle, and NX means the number concentration of the activated aerosol particles. So horizontal scale shows that's how the H parameter changed due to the seeding, and you can see that's how it's impact the amount of the condensed water. So we found a strong relation between the increase of the H particle and the amount of the condensed water. So it is one thing. And the other, and the figure B, shows that's the what is the relation? That's the ACB means the reflectivity, increase of the reflectivity due to the seeding 100 meters above the cloud base, and ACB plus 1000 means the increase of the reflectivity due to the seeding 1 kilometer above the cloud base, and we can find a strong relation between these 2 parameters. And what is the physics behind that? That's ACB plus 100 means that's how the diffusional growth impact the size distribution of the particles. And 1CB plus 1000 means that's if we take into consideration of the collision coalescence. So that means that we can increase the reflectivity 100 meters above the cloud base due to the more efficient diffusional growth. It will significantly impact the efficiency of the collision coalescence. And the last one, and here you can see that's the estimated effect of different type of particles, and so salt particle, nanoparticles, and the flare particles. So this whisper box means that if you compare the efficiency, we found the largest efficiency in the case of the nanoparticles. Sometimes it is similar to the salt particles, and the efficiency of the flare particles is almost negligible. And thank you for your attention, and sorry about that I used too many time for my presentation. Thank you.
All right, thank you, Ishvan. Due to some technical issues, we use more time than we expect. If you have any questions, I think we can address one. And then let's take another 5 minutes break and come back in 14:15 UTC. so that we can catch up some of the other small talks and the
Ronnie,
summary
I think
of
you are
our.
muted if you are speaking.
Sorry, I thought I'm not muted. Can you hear me? Hear me, right? Okay. Yeah. Sorry, I don't know what happened with my computer. It seems like we used too much time. So let's have a 5 minutes break and come back in 5 minutes. We'll have two short talks after that, and then we'll summarize our 4 cases after that. So thank you, everyone, and see you in 5 minutes. Yeah, sorry for the technical difficulties. So, Harish, when did the screen went off? Do you know? Oh, only a few seconds. Okay, it's something I don't know what happened to my screen. It seems like I have to. Sometimes I got disconnected from the platform, and maybe that's due to Wi-Fi or internet connection. Okay. All right. Thank you for the help. See you in 5 minutes.
Okay, funny.
This is really interesting, this thing.
Yeah, this morning I kind of disoriented a little bit when trying to find the presentation, but it's fun.
Oh yeah. Actually,
What's that?
it might be. Can you see me?
Yeah, I can see you.
No, I meant can you see my my video? I wonder if anybody else can. I think I'm going to hide it just in case. What's that? Is that? Around, so I'm going to leave the bubble. So I'll talk to you later.
Halo, otan jadwal.
All right, welcome back, everybody. Sorry for the short break, and hopefully everybody gets the water and foods and rest within the short time period. And we'll proceed with the next two short talks. The next one will be given by myself on the glaciogenic seeding simulation, and then Wei-Chai will give a talk on his new work on the CCN activation in a turbulent environment. And hopefully we'll wrap up within 15 to 20 minutes, and then we'll start our case summary. Let me share my screen. And can you hear me, by the way? Really? Can you hear me now? Okay. All right. Sorry, I thought I was spotlighted, but I don't know what happened. But hopefully everybody hear what I have to say. But welcome back to our coming session. And I'll give a short talk on our glaciogenic seeding simulation work. And Wei-Chai will be the next speaker. Let me share my screen. And I think it's shared, right? Okay, thank you. Thank you, Sandeep and Harish, for confirmation. This will be the 5 minutes talk that happened on August 5th on the ICCP, at the ICCP. So I will probably expand a little bit for 6 or 7 minutes. So title is Simulated Cloud Properties and Seeding Effect in a Snowy Case. So what is snowy? Snowy is stand for Seeded and Natural Orographic Wintertime Clouds, the Idaho experiment. It happened in 2017 from January to March, and we collect a lot of orographic cloud seeding related observations, not only environmental conditions, but cloud structures and microphysical properties. So it provides a complete set of data to constrain and evaluate models and to further quantify the seeding through observations and models together. And just an example for one of the snowy cases, snowy IOP5, we had the 2 seeding, airborne seeding in this region that gives you very clear seeding signals or seeding plumes being both observed from the X-band Dow radars and also the onboard of the aircraft, the W-band cloud radar. So the University of Wyoming King Air performed penetrations and collected great in situ and remote sensing data for this case. And we found this is a very complete and a good case for simulation. So we conduct our wet simulation using the parameterizations and schemes that we developed in the last decade. And here to show when the natural cloud forms as the white over the mountain, and if we release the silver iodide upwind, and it will pass over the mountain, nucleate ice, and then form snows. So we have all the processes included to describe the microphysical impact of AGI particles to the cloud. And we set up our model in these nested domains. On the left is our 900-meter grid spacing large domain encompassing the central target area in the black outline. And then we zoom in into a 300 and 100-meter areas domain, simulating these real case. And the aircraft tracks have been indicated by different color of lines. The blue lines indicate the seeding aircraft tracks. So the first seeding occurred here, and then the seeding aircraft flew over even further downwind and performed multiple seeding kind of operations, but only 2 of the seeding lines are observable and simulated. So here we also listed many other observational sites on the ground. I'll mention that later. And then to configure this real case simulation, we noticed in the past, based on our experiences, the results are very sensitive to the large-scale forcing data. So we actually ran this case with 4 different types of reanalysis, and only picked the right, or at least the most agreeable model results into LES simulations. And here are the total different simulations being conducted for this case, and with the descriptions on the right, changing different IN and CCM backgrounds, and also changing PBL, etc., to make sure we get the most representative simulation done in our sets of simulation. And here are 2 multi-panel comparisons. Shows on top is the W-band radar reflectivity from the University of King Air, and in the earlier flight before the seeding occurred, we evaluate 4 different types of reanalysis data, and we found only CFS2 and ARO5 are able to capture this double layer cloud with stable orographic cloud beneath the upper level. And also later on, when we conduct seeding, what we notice is that when the grid spacing is not fine enough, and we are not able to reproduce this 2 seeding line, only when we get to 300 meter and 100 meter grid spacing, we are now able to resolve this seeding morphology, the seeding plume morphology. Color shaded are all the snow mixing ratio area. So only main seeding effect occur within the seeded area, not within the natural cloud. And then we have to compare all our model microphysical and also other properties to the observations. And what we notice is that all the snowy earlier cases show very clean background. So observation indicate we have only about 20 per cc cloud droplet concentration during the flights. And if we use the regular aerosol concentration or climatology concentration, will give us a much larger overestimation. We have to scale down these aerosol inputs to simulate the reasonable clean cloud condition. And we also use the radiometer to evaluate our simulated liquid water pass, and so that the black line indicate the observation, and this period is where the seeding occurred. And we know if we have a more active ice nucleation parameterization, will simulate lower liquid water pass compared to others. And here is a summary of our seeded simulation. And each symbol, the color and shape of the symbol represent different rounds, and the number of the symbols represent the legs or the flight legs that we collect the ice or large particle concentration within the seeding plume. And here we have 7 legs that have these data. And we notice that for 900 meter simulation model, somewhat overestimate the ice or large particles within the seeding plume. But in the 300 and 100 meter, we're in a better ballpark within the factor of 2, that most of the concentration of large particles are within this range of uncertainties, so that we have better confidence that the seeding mechanisms actually work, and then agree with the observation. And with that, we evaluate the simulated precipitation on the ground, looking at the seeding enhancement. Someone has to be muted, I guess, and we are hearing some other noises or voices. Here we are comparing our precipitation on the ground from the 3 different gauges. Just want to mention that only when we get to the reasonable seeding rates and the grid spacing, we get better agreement, and then shows the seeding effect at the end. So here we want to demonstrate a way to really compare the model results with the observations in high detail. and then through this validation constraint, we can get more confidences in the outcome of our simulated seeding effect, so that the seeding kind of impact can be assessed through modeling framework in the future. Of course, ensemble approach will be needed, given that all the uncertainties are still there in both simulations and the observations. So that's all I have, and I think I saved some time. And if you have any questions, please raise your hand. All right, here is the Mahan.
Hi, yeah, hi. Hi, Lunin. This is Mohan from IITM.
Hey,
Hi.
good to see you. Go ahead.
Yeah. So, is it possible to separate the effect of large-scale circulation from the, when we see the cloud, from the model point of view? I mean, how to segregate the effect of large-scale circulation and the influence of seeding particle itself?
So separate the effect of large circulation and the seeding effect. Maybe, so the simulations that we conducted here is the real case simulation. So it's like we actually do a forecast or hindcast mode. For the more mechanism investigation, we're able to configure the model in a more idealized way to just look at the microphysical impact. And those work has been done by Ishvan and myself in the past. So we do have those idealized simulation scenarios. But then we apply the knowledge we gain to the real cloud to try to incorporate all the uncertainties and influences to compare to the real seeding effect. Just want to push it one step further to really evaluate these seeding program. So I think I might answer or might not answer a question, but hopefully that's useful.
Okay, thank you. Because those convective clouds, they are, I mean, once we seed it with glycogenic particles,
convective clouds.
they pardon?
Go ahead. Finish your question.
Yeah. I mean, those clouds are actually affected by large-scale circulation. So once we seed them, they kind of act as a feeder to the system. I mean, they activate more ice particles and more latent heating. And top of that, the large-scale circulation, they again affect those clouds, convective clouds. So is it possible from?
Yes, it is possible. We are planning to implement the piggybacking into the real case simulations, and for the cases that we simulated are more stable condition. So usually the error signals will not propagate upscale. So it usually shows some more cleaner seeding signals in our cases. But for more convective scenario, we have to rely on large ensemble or the piggybacking methodology to separate the dynamic influences in or tease out the signal from these interaction. So Tara, I saw your hands up. If you have very short comments, you are welcome to go. Otherwise, we'll move on to WeChat.
I just noticed that in your presentation, you are also showing some of the orographically forced effects there in your observations. It is kind of evident, right?
Right, we do see the orographic influences, convections, embedding convections, but for some cases they are not there. But for many of them, yes, the convections are there. Okay, thank you for the comments. And do you have more comments, Tara?
I'll ask you later.
Okay. All right, let's move on to our next speaker, Wojciech Grabowski. And Wojciech, just take it over. I'll save time.
All right, so I'm sharing my screen. I hope it will work.
Yeah, it worked.
Can you see it?
Yes.
Okay, so I hope it will be less than 10 minutes. Lulin, I wish you luck with your presentation at the 5-minute allocated spot, which actually will be more like 4 minutes if you think about all those, starting your presentation, so on and so forth. So I don't know. Anyway, so what I will be talking about is the activation, CCN activation, in a little bit different way than we've been thinking about it for decades, if well close to the 100 years, I guess. So this is actually a paper that is in review, and it's the first part of the work that we've been doing with Lois and with Bipin. So for my Indian colleagues, of course, you know Lois, you know Bipin. Others may not know them, but we're working together, and that's part of Lois' PhD studies. So we're looking at activation of CCN at the cloud base, and we're looking at the impact of turbulence. And initially, we're looking at just one CCN size. So let me remind you, you know this picture, you've seen it before, Raymond showed it. It's, if this is single CCN, this is the activation supersaturation. And then depending where the fluctuations, and those are different cases called in the caption, depending where the fluctuations are, then you may have either all fluctuations result in activation or only some. Of course, this is when the supersaturation fluctuation kind of is constant, like in the pi chamber. Well, of course, we know that at the cloud base, supersaturation kind of shifts to higher values and then comes back. Okay, that's the classical picture, as I will illustrate in a moment. So that's a different situation than in the pi chamber that we believe happens at the cloud base with turbulence. Let me start with some very kind of basic background. If you look at the CCN dry radius and then you look at the supersaturation activation in blue and then activation radius, this is very kind of 101 cloud physics, if you like. The smaller CCN dry radius, the higher supersaturation activation, and of course, the smaller the size. So in this study, what I decided to do is to just look at two classes. First of all, pick up the sea salt, and then look at two sizes, 10 microns and 200 microns. That's what I would argue is kind of sensible limit in natural CCN. Of course, we get sometimes larger, but then they often not get activated because for those large ones, the radius can be, in single or actually hundreds or tens of microns, and they may never activate. They just kind of follow the flow and grow. And then the smaller ones, as you can see, require really high supersaturation activation in excess of few percent. So just as an example, these two sizes. Okay. Now, the classical picture is that you take an adiabatic parser. So this is a traditional approach. And I've selected 3 updrafts, 1/3 of a meter, and 3 meters a second, and kind of sensible values that you expect a little bit below the cloud base, 97%, 900 hectopascals, 283 Kelvin. And then the parcel rises, so this is distance, and those panels show either radius or supersaturation. This is small CCN on the left, large CCN on the right, and lines here show you the activation, the moment that the activation happens. So, and those different updraft strengths. So, of course, the supersaturation needs to reach activation supersaturation. This is the activation supersaturation here. So you start with -3%, 97% relative humidity. It increases, reaches the saturation, it continues to increase, and once you reach saturation, you activate. And in fact, you activate all CCN, that's expected. If you have large updraft, the blue line, that supersaturation keeps increasing before the water take and latent heat release brings it back below. So that's the classical picture. So what turbulence can do to it? Well, this is the kind of a framework we're looking at. We're looking at the box, 64 cubic meters. That's a large box, 1 meter grid length, filled with turbulence. Turbulence is maintained in our simulations. And that's a turbulent adiabatic parcel, basically the same initial conditions, the same updrafts. And this parcel, think about this kind of a box that rises to the cloud base. So we start everywhere with 97%, those conditions, and we move up. And of course, the question is, what is different now comparing to the previous one? So first of all, this is kind of similar picture as before, But now for the supersaturation, I'm showing both the mean and the fluctuations. So I start with 0 fluctuations, but of course, before I get to the saturation, then kind of build up, because this is kind of dry air that is turbulent, and supersaturation can be there, and it can be quite high for this domain. If you chose a smaller domain, these fluctuations will be smaller. Okay, so a couple points to notice. First of all, supersaturation doesn't have to reach activation supersaturation, for example, for the small updraft, because you have large fluctuations, and that's enough to activate, and actually activation starts earlier before you reach supersaturation, as you can see. Now, for this small updraft, you activate only a quarter of available CCN, so that's surprising. And the reason is, I will explain in the next slide, that basically some CCN avoids activation because it turns out to be in those areas that supersaturation fluctuations are lower. And of course, for large updraft, you do go above the supersaturation, and fluctuations are smaller. And the reason why fluctuations are smaller is also well understood, because you just go faster. So you have less time to develop those fluctuations because you start with 0. So this is the key. Another key point is that the spectral width, I mean, in the other case with the adiabatic parser, it was 0. There was no, all droplets have the same size. Look, now you can have 1 or 1.5 widths just because you activate at different moments. So this is the picture that illustrates that. If you just, I mean, this is stronger updrafts, weaker updraft, small CCN, large CCN. But if you look at just small CCN and small updraft, this is what happens. They activate at different times. This is reduced, so they kind of go, activate, and then droplets grow. But many of them just don't activate. They are lucky or unlucky particles, CCN if you like, that avoid activation. So you get growing droplets, or you get CCN that avoided activation. And interestingly, those avoiding activation can be large, because in this single size CCN, you get quarter of those when you get very slowly, and those particles avoid activation. So droplet spectra, again, those are small updrafts, large updrafts, small CCN, large CCN. Let's just point out that if you get small CCN and small updrafts, look how wide this spectrum is. Tremendous. It's unbelievable. It has over a micron width, but you can see how those tails reach out. And of course, those unactivated are here. This is linear scale. This is the logarithmic scale. And you can see that this width is significant even for large CCN with small updraft. So the conclusions, this is first of all work in progress. I have to remind you, and the turbulence can have a significant impact on CCN activation. I would say surprisingly significant impact. In contrast to the adiabatic parser, some CCN can activate early, and some can avoid activation entirely when small-scale turbulence is present. And I have to say that details of the impact depends on specific details of the presented simulations. For example, domain size, TKE, initial conditions, CCN, so on, and call for more research in this area through very high-resolution modeling, not the one that I'm kind of showing, but rather something like our congestus case that is run, let's say, with 1 meter grid length. So the turbulence of the volume going through the cloud base is directly simulated, rather than kind of an approach that is basically a mimic. And perhaps significant point, this is a kind of a comment towards Raymond, that this situation that we consider here is different than in the pipe chamber. And it calls on the observations, perhaps, for the facility similar to pipe chamber, but with decreasing pressure, because of course the driver the driver of the decreasing temperature and of course decreasing pressure as well is the expansion of the air when the parser rises. So it would be great to have a pipe chamber within a bubble, if you like, with expansion chamber. That would be kind of conditions that may resemble the cloud bay activation. So I think the first point here, that turbulence can have significant impact on CCN activation, is something that that I would like you to keep in mind. So thank you very much. And if there are some questions, I can answer them. And of course, I expect that some of you may be reviewers of this paper.
Okay, thank you, Wojciech. Alexi, you are spotlighted. You can unmute yourself.
Yeah, Wojciech, nice presentation. Thanks. Just numerical simulation shows that if you do not activate enough CCNs at the cloud-based slow ascent, later on inside cloud, when those low activated CCN parcels will be picked up by high updrafts, there will be a secondary secondary nucleation, and basically it kills the entire effect. So there are some publications regarding this matter.
Yes, of course. And we look into that in completely different studies. Kamal had a paper, I have a paper. My student 10 years ago had a paper about activation, about the cloud-based. This is well appreciated, and there is no question about it. There are, of course, other effects like the updraft across the cloud-based changes from the middle of the cloud to at edges. So, of course, at the edges, you have different conditions for activation. So, yeah, those are kind of real-world issues that one has to appreciate. But the point here is that if you think about activation through the adiabatic parcel, that requires some revision, if you like, some different thinking at the end, and hopefully we will get to the bottom of it, in subsequent work. Yep.
Jason, you are spotlighted. Go ahead, unmute yourself. Jason?
Oh, is that for me? Sorry, Lilin.
Yeah, now it's yours because I saw your hands up.
Yeah, we can hear you.
Lilin, are you, somebody said there's...
I can hear you, Jason. Can you hear me?
Sorry, I wasn't sure if I was up.
Okay.
Wojciech, yeah, nice presentation. Hugh told me that I would be blacklisted from this workshop if I mention NWP, so I won't. But do you see this work potentially leading to a parameterization of activation that could be applied in mesoscale models? Like, say, 1 to 3 kilometer models that are running double moment schemes?
Yeah, potentially, yes. It's probably a stretch. I think we are kind of beginning, I have to admit, beginning on the modeling side and PyChamber observations, the effects of, starting to understand the effects of turbulence on activation and other cloud processes. So it's eventually I agree, but I don't see kind of a clear path, at least not now, at some point, because there are so many parameters, at least because there are so many parameters that control the outcome of those, highly idealized simulations. That's how I would reply to that.
Thanks.
All right. I think we need to move on. I saw Tara's hands up. If Tara, you have any comments, you are welcome to say now.
Yeah, thank you, Lulin. I just wanted to ask Wojciech why your size distribution has only one peak. You are not having any secondary activation or?
No, because I thought that we need to understand what happens kind of similarly to the PyChamber. What happens if you get only one size? What impact it has? Because if we understand that would help us to understand in simulations with a spectrum. And in fact, we're running the simulations with the spectrum right now, and I can tell you that this is the correct way of doing things. Understand a simple system to kind of understand what's going on in the more complex system. So that's the simple motivation. And the second paper is kind of, the simulations are being run and the paper will be coming up at some point, yes.
Okay. Final comment or question from Sudarshan, and then we'll move on.
Yeah, hello, Wojciech. My question is regarding the effect of updraft on activation. And from this simulation, you are getting like spectral broadening as well as larger droplet for lower updraft velocity, right? So what is your suggestion for cloud seeding experiment? Should we seed like when a region of low updraft so that we can get maximum spectral broadening and larger doublet?
Well, Sudarshan, I will not go and speculate how this is linked to the cloud seeding. So I mean, we can talk about it offline, but I don't think, it's too early to tell. I mean, I was just surprised that you get, with smaller updrafts, you just activate a relatively small fraction of CCN. So let's leave it like that. Don't go too far beyond we get understanding what's going on here. So that will be my answer.
Okay,
Thanks,
and another
Sudarshan.
question is, so in your parcel with turbulence, so what is the main difference between DNS and this parcel with turbulence?
Oh, this is, you can think that we're doing DNS. We don't call it DNS, we call it scaled up DNS. In other words, it's turbulence, but the dissipation is high enough to kind of kill energy at 1 meter scale. Let's not go to the detail. Ask Lois for a paper. The paper has been written and published some time ago. And I think it's a correct approach to kind of go to bigger domains. And anyway, let's not take any more time on that. Thank you.
Yeah, thank you. Thank you, Stassen. And Weicha, would you unshare your screen, and we'll move on to our final section on the about the workshop. So that will be the summary of all our cases. So I don't know if Steve or CC are ready. So please, one of you will come up and show the summary, and then we'll proceed with the order. Next will be single congestors, and next will be COPE and CIPEX. Thank you.
Okay, so can you see my full screen?
Yes, we can hear you and can see the screen.
Okay, thanks. Yeah, first I want to thank the Monday's for everyone who attended Monday's discussion. This was my first cloud modeling workshop, and it was a pleasant experience. Though I really prefer to have an in-person one in Pune. The bright side of the virtual meeting is that we can reach more people. Apparently, we had more than 100 attendees on Monday, which was pleasantly unexpected, and which also blew up the platform. So thanks IITM to fix this issue quickly after the first day. And for the PyChamber case, we have 7 groups from different parts of the world that contributed to the comparison, and they have been listed here. And also we would like to give our special thanks to Raymond, Will, Prashant, Subin, and the entire PyChamber group for their continuous help. So before this one, we had a mini workshop last November together with the congestors case. This workshop helped us to modify the case description to better constrain the simulations. As this is a continuous effort, we will keep the conversation going, and we welcome new modelers to join the discussion and the comparison. So please contact me or Steve if you want to be part of this conversation. So the geometry, so here is just a very quick overview of this case. The geometry of the PyChamber is illustrated on the right. The temperature difference between the saturated top and bottom walls generate turbulence and supersaturation. So aerosols are constantly injected to form droplets. The purpose of this case is to simulate the microphysical response to different injection rates during the steady state period. We have 4 different LES to simulate the entire chamber, 1 DNS for the chamber, 1 DNS for the core region, and 1 DEM-PM to join this comparison. So we compared the different microphysical and the thermodynamics variables. Here just showed an example of the time series of domain average of some microphysical variables from the 7 models. I won't go to the detail, but we can already see for the same variables, so we see discrepancies between the models in the chain and the magnitude. This was the first intercomparison study on the cloud chamber simulations. So the comparison was performed among a diverse set of model geometries as well as various microphysics schemes. So in summary, we found that the model inhabits different regions of mean supersaturation and fluctuation space. It will be interesting to know what regions the real pi chamber inhabits. We also found the droplet size distribution simulated by the most models are generally consistent with the theoretical prediction that considers the impact of mean and fluctuating supersaturation. So nearly all models show both mean and fluctuations are important. So we also found that the processes that determine the microphysics, such as liquid water content, DST shapes, number concentration of droplets, etc., remain poorly quantified in the simulation. Lastly, we also see the model results exhibit numerous differences that are not well understood and will need future work. So for our future plan, we would like to obtain more measurements from the pi chamber to evaluate the model results. Some examples are listed here. We would also like to further analyze the wall fluxes and the particle settling timescales, which is important to understand the model differences in both the thermodynamics and microphysics. Lastly, the role of large-scale circulations is also an important topic, and analyzing the Lagrangian particle growth history would be valuable to better understand the aerosol activation and settlement in the chamber. So thank you.
Thank you, Cici, for the high-level summary. It was nice to see so many good discussions. And let's save time and move on to our second case, and we'll see if any questions at the end for different cases. So who's the second one? Shinichiro? Okay. Floor is yours.
Okay, let me share my screen.
Yes, I can hear you.
Good.
And I can see the screen.
Thank you. So you see this PowerPoint slide?
The full screen, yes.
Good. Let me summarize our case on single cumulus congestus case. So the numerical setup is almost the same as Lasha Trapetto 2005, and this is based on the SCAMS campaign. You can find the detailed description on the website of this MIP project. And if you are interested in, please also take a look at the VR, virtual reality movie on the YouTube. This is from the same case, but a little bit higher grid resolution. Delta XYZ is 10 meters for this simulation. But for the case study, for our case study, we specify the grid resolution to 50. This is a summary of the key objectives of this project and the scientific questions. So the key objective of this study is to compare the beam and particle-based cloud microphysics models in a realistic turbulent flow of a single cumulus congestus cloud. And the questions are, is the broadening of droplet size distribution due to turbulence well captured by these schemes, and is the surface precipitation consistent between the two schemes, and what is the impact of numerical diffusion of beam schemes and the computational costs of two types of schemes. This is the list of participants. So CM1 have tau beam model and SDM particle-based model, and OILOG has 2Me SDM model and a beam model. We also have scale beam, scale SDM, UW LCM, and WAF HUCM and WAF UPNB. And this is, I think, the highlight of this study. So we compared the vertical profile of the droplet size spectrum width. And here we found that the spectrum width is consistently bigger in beam models and particle-based models. So the pink lines corresponds to 3 microns, and you can see that beam model, all the beam models spread, the width is larger than 3 microns, but in all the particle-based models, it's less than 3 microns. I think this is a highlight. And this is a summary of our findings. So from the control case, this corresponds to a relatively polluted aerosol case without collision coalescence. And here we confirm that beam and particle-based models compare well qualitatively, and it's consistent to what we observe in nature. And as I mentioned, the droplet size distribution predicted by the droplet size distribution with spectrum widths predicted by beam models are consistently wider than particle-based models. We, after the discussion on Tuesday, we conjecture that this is due to the numerical diffusion of beam schemes, but okay, this time due to the coarse vertical grid resolution. So this is a little bit complicated problem mechanism, but we have to transport liquid water in a multi-dimensional space to the radius space and also to the real space to XYZ direction. So it's a multi-dimensional transport. So to suppress the numerical diffusion sufficiently, we have to use fine enough grid resolution for all the direction. And as I pointed out here, it seems for this grid resolution we tested, the 30 beams or more would be sufficient for good numerical convergence in this direction, in beam direction, radius direction, or mass direction. So from this, we conjecture that this numerical diffusion is caused by the coarse vertical grid resolution, and this is what consistent with Morrison et al. 2018. And there are another possibilities. One would be the big fast beam, too big fast beam, and another possibility would be the lack of numerical diffusion of particle-based schemes. So lack of numerical diffusion in particle-based schemes is a salient feature of particle-based schemes, but to simulate the phenomena accurately, we need to consider the subgrid scale turbulence. And it's all ignored, at least in this study. So maybe we are underestimating the droplet size widths in particle-based models. So there are several ways to explain the result. So we need to work more on this point in the future. And another finding is that the liquid water content in a grid cell can be larger than the adiabatic limit in particle-based models, especially in the tails. And we confirmed that this is due to the randomness of super droplets. And we also tested lower number concentration of aerosol particles and its impact to precipitation, but we do not have enough amount of data yet, so we couldn't draw any clear conclusion yet. So at least we found that scale STM and UWLCM, both particle-based models, do not agree well, and not enough data for beam models. And another finding is that for discrete resolution, it seems beam number is larger than 30 would be sufficient enough. And for particle-based models, 100 super droplets per cell seems to be sufficient, so it is still noisy. And the computational cost seems to be comparable in both schemes. So this is the possible future plan in my mind. I definitely have to consult with all the participants, but I think we have to do some more in detail investigation of the wider droplet spectrum of beam models, and also more analysis on precipitation. So I think I have to consult Yosuke Sato first, but I think we should do some preliminary analysis using scale bin and scale STM, because those two have the same, almost the same dynamical core, so the comparison must be easy. So using these two models, we assess the impact of the vertical grid resolution, beam, super droplet numbers, and the fast size of the fast beam. And I also would like to ask Kamal, if possible, if you can do some similar analysis using your CM1 model, because you also have two types of schemes, the beam model and the particle-based model. Then after this preliminary analysis, I would like to ask all the other participants, or all the other beam model participants to run a limited number of experiments to finalize our conclusion. And I also would like to ask, especially beam model participants, to run a case with precipitation. And I also like to ask Kamal once again, using your CM1 STM model, to run a case with precipitation. That's all from my side. Thank you very much.
Thank you, Shinichiro. Let's move on to next, and then we save the question at the end. Okay, our next case is the Cope case. Yeah, Sony is there. Perfect. Yeah, I think the screen is unshared.
Okay, can you see and hear this?
Yes, I can see it.
Okay. All right, good. So this is, hold on. Okay, this is case 3. It was a line of deep convection and strong vertical wind shear based on the 2 August Cope case. Myself and Holly Mallison here at the U of I were the organizers, and I had already published the CM1 NSSL run. And then we had 2 other groups of participants, Tunbo Han from KIT, who ran the Icon 3D model with 2-moment bulk microphysics. And then Jan Nicholas Wells and Axel Seifert of the German Weather Service had submitted 2 simulations, both with Icon 2D, with bulk double moment microphysics, and then with MC Snow. So we had 4 simulations total to compare here. So the summary of our findings, we were looking at the influence of the deep of the shear on both precipitation and then also on rime splintering, Hallett-Mossop process. So the results that we found with respect to precipitation was that, of course, the strong wind shear could influence the amount reaching the ground. In the stronger shear, the updrafts can tilt with height. And in that case, the precipitation formed at the tops of the clouds, as it falls towards the ground, it doesn't really get to accrete and collect as much cloud water. And so the total flux of water mass to the ground is decreased. And that's shown in the two drastic examples here on the right by the solid line, where the maximum rain rates were quite low for this case, for both the examples shown. And all the models, including ICON 3D, which is not shown here as well, predicted small precipitation rates in this strong shear. The 3D models were like less than 10 millimeters per hour maximum, and the 2D models were less than 5 millimeters per hour maximum. The biggest differences in the precipitation occurred in those models where as I was explaining, that updraft tilt was occurring. When that happened, then you could either get some cells that were strengthened when you decreased the shear, like the CM1 model shown in the upper right, where we got much higher rain rates, or in the ICON 2D in the lower right, it even some initial greater precipitation output then excited new cells. So that's when we saw the biggest differences in the strong shear and the reduced shear runs. Secondary ice production, now turning to that theme, we looked at rime splintering, and I don't know if this came across during our discussion, but I wanted to pull this together, that it was really comparable across all the models if you compared it for similar amounts of updraft tilt with height. So when they had less updraft tilt with height, the models all predicted rime splintering in about, say, 10 to 100 per liter of extra ice that was distributed to mid-levels in the cloud. So kind of shown here below in the ICON 3D example, in this black box in the rime splintering zone, we saw a lot more ice. And then when we turned off rime splintering, all of that goes away, as well as a significant amount in the upper part of the cloud as well. And that was consistent in all the model runs. So other findings and future work, etc. We had a nice long discussion because different models had the clouds initiated by different forcing mechanisms. Our original runs had used the surface heat flux, and that was not available in the other models. So we had tried to produce a line of bubbles to kind of mimic the effect of the surface heat flux. But I think we all kind of agreed that was not as successful as we would have liked, that it actually greatly influenced the updraft characteristics in these clouds. They differed in width, in depth, strength, and even the tilt with the height from the shear. And so that really dominated the results. And so we decided that really that would be an interesting result to continue to explore together as well. But to do so properly, we would need to create some more simulations like with the same model, but using both kinds of forcing. And then also using the same model with one kind of cloud forcing, and then having the additional microphysical schemes to look at as a secondary factor. So this feeds into our plans. It looks like I need to do another CM1 simulation and initiate it with warm bubbles instead of the surface heat flux to kind of help quantify that influence. Axel has offered to try to add NSSL scheme to ICON so that we can kind of compare different schemes in the same dynamical framework and really look at the rime splintering differences a little bit in a more clean way there. Now, I also, I think we all agree we need some more simulations here. I've listed some potential collaborators here. I don't want anyone to feel like I'm picking on them. They had just expressed interest here during the discussion. But if you've had second thoughts or whatever, I'm not holding you to it here. I just wanted to document that you were interested so I can reach out later and send an email. So we had talked about the addition of a WRF simulation, say with NSSL microphysics, and then maybe some other microphysics as well. Lulin, and I'm sorry, Lulin, I couldn't remember the name of your collaborator in China, but I know there's some interest there. And as well as Sandeep, who's been working with Tara, has expressed some interest to me as well using WRF. So maybe we can get, yet a few more simulations here. Other potential participants, Jason had also expressed maybe some interest, as well as Hugh when they get piggybacking working in CM1. Again, I'm not holding anyone to this. I just kind of wanted to document that. And with that, I'm done. Thanks.
Thank you, Sonia, for the great summary. Yes, we do. We do have more collaborators around the world who would like to contribute to it. Yeah, I won't name the specific name, but at least Chunzong is here, and Chunzong can be part of that if he wants. And let's move on to our final case. That will be the Kypex. Dustin is ready.
Hi, can you see my screen?
Yes, I can hear you and can see your screen.
Okay. So for summarizing Kypex case study, the main objective of this case was to investigate the effect of aerosol in deep convective cloud under different monsoon environment. And this case was led by myself and Gayatri. And these are the list of case participants, which is written below. So this is the summary of various model simulation from this case. So total 7 simulation done in WRF and other model using LES bulk and bin scheme, and as well as WRF CRM model. So in different there are various domain size and resolution and done during the simulation. Different CCN cases are done, like starting from 100 up to 5,000 in some simulations, and various microphysics schemes are used. Some people used radius only as the initialization, and some people used DN and D2 domain mean sounding. So main focus of this study was to investigate like effect of aerosol or CCN on rainfall, monsoon rainfall. So in some model, I will say in most of the model, we found that actually rain is increased by high CCN, except one model. So let us move to next. Just I will present a few important results from this case. So this analysis is done by Gayatri, and she is looking this combined effect of moisture and aerosol using WRF bin microphysics scheme. And these are various cloud parameter like supercooled liquid water, ice water, snow water, gropel water, and updraft maximum speed and precipitation. So the main point is that when she varies the initial sounding, like for moisture content of the environment, like -20 to up to +20, so total 5 moisture conditions, and she ran the model with 2 different CCN. One is 100 and another is 3,000, I think, that is representative for clean and polluted condition. And the most important finding is that the impact of moisture is more significant compared to aerosol on precipitation or other cloud parameters. So always there is a positive effect when there is an increase in moisture, total rainfall and other cloud waters and updraft speed, all are like they are positively increasing. However, when the polluted condition concern, there is a further increase compared to clean case. So this is from another model simulation from ICMW, that is Metopis NERC cloud model. And actually this model has a relatively opposite response, and it produced negative effect of CCN on rain, but there seems to have a positive effect on liquid water path and ice water path. So one simulation done to compare bin and bulk microphysics, and they found that bin microphysics is better and it is making more rain compared to bulk microphysics. Another study done to investigate the effect of wind shear on monsoon cloud using WRF CRM model, and they found that with decreasing wind speed, it decreases liquid water content and cloud fraction, and that indicates that wind shear plays a dominant role in cloud development in the monsoon environment. So there is another study I have done to investigate effect of moisture on cloud fraction and mass flux. Mass flux is kind of dynamical parameter of the cloud, and we found that with drier environmental condition, mass flux decreases, and as well as entrainment rate decreases. So these are the major findings from this study. Higher CCN produced enhanced rain in most of the condition, but cloud depth and liquid water path are relatively similar in all model. Higher precipitation is achieved with increasing moisture also in the initial sounding. Impact of moisture is more significant than effect of CCN. One model studied the importance of Hallett-Mossop process, ice microphysics process using spectral beam microphysics. And some other model found decrease in environmental relative humidity leads decrease in that is already mentioned entrainment rate and mass flux. Cloud core updraft seems to be strengthened in dry condition compared to moist condition. And there are some other finding that enhanced CCN actually delays the onset of rainfall in this model. However, lower CCN generate quick and intense precipitation in Monk model. Beam microphysics leads a higher domain average accumulated rainfall compared to bulk microphysics. And wind speed play important role, and it has negative impact on liquid water content and cloud fraction in WRF model. So with all this major finding, now I move to the future plan that we may be able to do in future. So the the plan is that we need to do the intercomparison of different model with the same configuration. And because in the recent situation, several people have done with a different configuration, so we need to do further work on that. And a detailed intercomparison of various processes in a bulk and beam microphysics will be done in future. And another thing that I want to carry out in future is to investigate the effect of CCN on entrainment rate, which is kind of insensitive in the present setup. So in the next simulation setup, I want to include radiation scheme and want to study different microphysics scheme. And I think that's all from my end. Thank you.
Thank you, Sudarshan, for the nice summary. And now we have all the cases summarized, and we open up the floor for our audiences and participants to for questions and comments. And we will conclude and adjourn our meeting probably in next 10 minutes. So any thoughts, any comments, very welcome to share with us. So can you hear me, everybody? Today I think my connection is not as stable as yesterday. Okay, good. Thanks for the thumbs up. Yeah, any specific suggestions? And also, anyone wants to join the kind of the discussion and cases, you're welcome to reach out to our case leaders. And our meeting, the whole full weeks of workshop have been recorded through YouTube and also the screen recording. So these contents will be available online through our IATM channel, and will be free for everybody to check in the future. So let's see if we have any thoughts, comments, and suggestions. And I would like to, if no one raised the hand, I would like Tara to say some words, probably concluding our workshop, and I'll let Sandeep and Harish mention any other pay attention items. So Tara, go ahead.
Thank you, Lulin, and I want to thank each one of you who are present here and who were here platform.
Yeah, Tara, you are a little bit broken
up. You were kind enough to bear, but I think it has have this conversation. Yeah. So 1 second. Yeah, I think. Hello.
Yes.
Hello.
Yes, we can hear you. Yeah, I can see the signal bars. Tara's avatar is below. Yeah, I think the connection was not loose today. But let's wait while we're waiting for Tara to come back. So Sandeep and Harish, do you have anything wants to announce before we adjourn the meeting?
Yeah, hello.
Yeah, Tara, you're back. Yes.
Yeah, sorry about I had lost connection a little while. Yeah, I want to thank I want to read what I said. I want to thank each one of you who were here, and there was difficulty in the first day, but that difficulty has led us to do this live streaming, and it is going to help many others who were not here, and it is going to help others in the future who will be interested as well. So I think it gives us more hope and opportunities, although the situation is difficult, and but these two guys, Sandeep and Harish, they have been working hard to make all the things possible, and I want to thank them also, and all the others who attended, and especially Lulin and all the speakers, and all the case leaders, all the speakers, participants. Thank you.
All right. Thank you, Tara. And it was, I think it was a great experience for me, and to meet everybody on this platform. And I do want to express my sincere appreciation to Sandeep and Harish for your great support. And I will applaud here and for you, and you are our hero. Yeah, thank you. And then with that, I think we can adjourn our workshop. And you know how to reach out to us, so please send emails and all kinds of ways to reach out. And we saved the rest of the time for you to look at the posters and wandering around. And for all the case leaders, please let's move to the breakout room, discussion room. That's the common breakout discussion in the upper right corner, upper left corner outside of this room. So let's meet there in 2 or 3 minutes, and then we gonna summarize our workshop there. So thank you, and see you there soon. And for the rest of our participants, thank you, and we'll see you in the future. Bye.
Thank you.
Bye.
Bye. Everyone register on the guest book also.